All right, let's recapitulate the salient points which were dwelled upon yesterday in discussion class. And as necessary, talk about a couple of considerations which you may not have gotten to in discussion class. With this, you should be raring to go for this activity. And early birds, only a couple of you. I think I've reminded you about this, but if not, D309, if you're taking the exam today at 2 to 4 p.m. or 4 to 6 p.m. The rest of you folks, well, if you can't find this, there's nothing I can say. Get out your GPS or something. And yes, I will invent BQ3. Now that I know where we're at, so I'll invent this tomorrow as necessary. If I don't have it done Friday, I'll finish it Friday, so that BQ3, I guarantee, will be ready for your entertainment by this weekend at the latest. To repeat, most of chapter 23 is devoted to the issue of recognizing how we can establish rationale for the assessment of Bronsted-Lowry acid-base strength. Not necessarily quantitatively, because the only way you can really find a Ka value, for example, is to go to the lab and do experiments. But qualitatively, for sure. Why is this acid stronger than that acid? The way we play the game, as you already know, is to assess the effective negative charge density of the conjugate base of each acid that's in question. Because when we know the relative strengths of the conjugate bases, in turn, we know the relative strengths of the conjugate acids, which will be in reverse order relative to the strengths of the conjugate bases. Just as what the acid-base table arrangement depends on. What are the factors? Number one, charge to size, which is why we started with chapter 23 by reminding you, take a look at the videos which follow from what you should have done in 2045 on understanding periodic size trends of atoms. Why is HCl a stronger acid than HF? Well, conjugate bases, fluoride ion, chloride ion. Given that HCl is a stronger acid than HF, it follows that fluoride ion is a stronger base than chloride ion. Why is this true? Notice that. Fluoride ions derive from fluorine, the most electronegative atom. Much more electronegative than chlorine. If I try to rationalize the difference in strengths between HF and HCl on the basis of electronegativity alone, which acid will I predict to be stronger? Based on electronegativity, which of these acids would I predict to be stronger? HF. Why? Fluorine is much more electronegative than chlorine, which means on the basis of electronegativity, the negative charge density on fluoride ion should be stabilized to a greater extent than the negative charge density on chloride ion. Does this fit the facts? No. The facts are that HCl is a much stronger acid. So we got to go someplace else beside electronegativity. So if you did not recognize this yesterday during discussion class, recognize it now. Recognize it forever as you continue to study any aspect of science. For rationale of a problem, of a quandary, of a question, you may have to consider a number of pertinent factors. And some of the factors may disagree with prediction-wise with other factors, like this. The electronegativity argument would predict HF to be the stronger acid than HCl. That ain't true, because there's only one bottom line dictator in all of this, and that's the experimentally verifiable fact. Once we know HCl to be a much stronger acid than HF, we got to look beyond electronegativity argument. So we go back to charge to size, and we recognize chlorine is a much larger atom than fluorine. These are atoms in the same family, but as you proceed from period to period within a family for A family atoms, the general size trend observation is that the lower period atom, like chlorine versus fluorine, is a much larger atom, which follows from the stuff that I asked you to look at on the videos. On this basis, I'm looking at smearing a negative charge on the surface of a chloride ion. Let's say that's a basketball. Compared to smearing a negative charge on the surface of a fluoride ion. Let's say that's a softball. Believing that you know what the relative sizes are of a basketball versus a softball. Basketball, softball. With no other factors being considered, the larger the surface on which I smear a negative charge, the more dilute the negative charge. The more dilute the negative charge, the more stable, less reactive is the negative charge. The more stable, less reactive is the base. And the conjugate acid will be therefore stronger. Does this argument fit the facts? For HCl being a much stronger acid than HF? You're damn right. So that's the one I pick. Now notice that that allows us to establish a rationale for the relative strengths of the halogen acids, HF, HCl, HBr, HI. Of these four, as you recognized yesterday, even though HBr and HI are not contained in our acid-base table, would they be listed as strong acids? You're damn right, because we now recognize they're stronger than HCl, and that's a strong acid. How about HF versus water? Acids derived from neighboring atoms in the same period. Molecular acids derived from neighboring atoms, specifically oxygen and fluorine in period number 2. Well, the conjugate bases are hydroxide ion and fluoride ion. From the acid-base table, if nothing else, we know hydroxide ion is a much stronger base than fluoride ion. Why is this true? Well, let's try the charge to size ratio assessment. Which atom is bigger, oxygen or fluorine? Oxygen. So which anion is bigger, hydroxide ion or fluoride ion? Which anion is bigger? Hydroxide ion, which is derived from the larger atom oxygen? Is hydroxide ion bigger than fluoride ion? You're damn right. Well, on that basis, I'm going to expect hydroxide ion to be a, you fill in the blank, weaker or stronger, base than fluoride ion. Weaker. Is that true? No. So I got to go someplace else. So now I'll reconsider electronegativity. Because we know for atoms in the same period, particularly if they're neighboring atoms, there is not that much of a size difference. Not nearly the likes of which you observe for fluorine compared to chlorine. Oxygen's bigger than fluorine, the atoms, but not a whole lot bigger. And that argument, charge to size ratio argument, doesn't work. So now I recognize that the electronegativity of fluorine is 4.0, the greatest, whereas the electronegativity of oxygen is 3.5. Still rather substantial. But when I look at the facts and say that based on electronegativity, I expect the fluoride ion to be a weaker, more stable, less reactive base than hydroxide ion, and I say, does that fit the facts? And the answer is, you betcha. That's the argument I use. How about that? Because one of the things, if nothing else, that I hope these considerations bring to your attention. There are practically no absolutes in the world of science. We will always, if we're true scientists, continue to look for better and more thorough and penetrating explanations of any problem. You've got to watch out for these things called laws. Law is just a theory which seems to have worked all the time. But if somebody ever comes up with an exception, then what's going to get modified? The exception or the law? The law is going to get modified. Then induction, which we in brief told you about on Monday, and you looked at this yesterday, is really an idea of electronegativity, which interestingly enough is a property that extends through a covalent bond network, a covalent bond skeleton. Example, trifluoroacetic acid. So named because of these 3 fluorine atom substituents on this carbon atom. Versus acetic acid. We can see that structurally these things are identical. Compositionally, they're identical except for these 3 peripheral hydrogen atoms compared to these 3 peripheral fluorine atoms. Now, when these things do their acid thing, we wind up with the trifluoroacetate ion versus the acetate ion itself. And we know that resonance will provide stabilization of this negative charge density. But if that's the only factor, if these 3 fluorine atoms don't exert any stabilizing effect at all on this negative charge, how will these bases compare strength-wise? They will be what? Identical. Ha-ha, but they're not identical. Trifluoroacetic acid is a much stronger acid than acetic acid itself. So now we've got to wrestle with the fact that somehow, some way, these fluorine atoms, which are part of this species but not part of this species, exert a stabilizing effect on this negative charge. It's called induction. It is as if, because of the extreme electronegativity of the fluorine atoms, this negative charge is drawn toward the fluorine atoms. And the more effectively this negative charge is drawn toward the fluorine atoms, the greater the smear of the negative charge. The more you smear the negative charge, the more you dilute it. The more you dilute this negative charge, the weaker and more stable this base becomes, which in turn makes its conjugate acid ever so stronger. That's induction. Now then, the next issue was, does induction depend on the proximity of the atoms of appreciable electronegativity from the site of development of negative charge? That's a long sentence. Did you get it? Let's take a look at pictures then. We've got trifluoroacetic acid considered here. We're going to throw this one into the mix. This is trifluoropropionic acid. If I cared about the name, I'd write it down. I don't. You can play with the names in organic chemistry. Organic chemistry is a blast, but I'm not a big fan of names. So in that respect, I wouldn't be a good organic teacher. Because once I got the formula on the board, I got what I want. And what its name is, I hardly give a damn. It's like you. What I care about is how well you do, not what your name is. That doesn't mean anything to me. In turn, my name shouldn't mean anything to you. I mean it. What I offer you in this gathering is what counts. Now, how pretty I might look, or ugly as the case might be, What counts is the chemistry and the understanding associated with such that I try to offer you. And if you think that's not good, you should so say on the evaluation process. But if you think it's good, I hope you speak up and say so. I will tell you, since I'm reflecting on this just for a moment, there's only one seriously disconcerting aspect of evaluations from students to me. And that is, when we did these things in writing, so I got these things back, and now I can see most of them on the web. Students saying that I was a mean, no good son of a bitch, as demonstrated by the fact that when they came to see me in my office, I belittled them. I insulted them. I treated them as if they were inferior beings. Students said that. And I said, what the hell's going on here? You're damn right I hold you accountable for showing me what you do or do not understand, but I don't do that. And then one term I kept track of the number of students who throughout the term came to see me. That's all I did. How many students came to see me? There's about 20 students and about 20 different names. You know, I don't know if you come to see me more than once, I don't write your name again. Okay? At the end of that term, there were over 50 students who said that on the evaluation form. I said, that's quite nice. I saw 20 students and over 50 said this. You think I'm going to pay much attention to this stuff? No. But does the administration of this place pay attention to that? You're damn right. Because they don't know what I know. That being that only 20 people came to see me and over 50 said this. If the administration is going to take that as a discredit of me, then they don't know what the hell they're doing. I'm serious about that. And that's not fair. On we go. This acid loses H+. There's the base. Here's this base. Remember my smearing arrows? I think you remember what this is. Notice that. If these fluorine atoms are as effective as these fluorine atoms at drawing this negative charge toward them by induction, this negative charge would in fact be smeared over a larger surface, wouldn't it? Because this is a larger species. It's got a CH2 group in here. And if this minus charge is smeared over a larger surface, will it be more concentrated or less concentrated? That means this base would be more stable. And the corresponding acid, conjugate acid of this, would be stronger than this. But that isn't true. This acid is a good deal stronger than this acid. The Ka values compare by a factor of about 10 cubed. That means this acid is 1,000 times stronger than this acid, more or less. This means that in order for highly electronegative atoms to effectively stabilize negative charge density by induction, they got to be pretty close to that minus charge. This is already showing us that for this species, these highly electronegative fluorine atoms are 1, 2, 3 atoms removed. There's the minus charge. Here, the fluorine atoms are 1, 2, 3, 4 atoms removed. Only one more atom. Does that have an impact on inductive ability? You betcha. It's extreme. So right off the bat, we can make the generalization. The highly electronegative atoms need to be no further from the site of negative charge density than 3 atoms. Do you think then that this oxygen atom provides negative charge density stabilization on this negative charge? Is oxygen fairly electronegative? Is not oxygen number 2 compared to fluorine? So this thing is also stabilizing by induction and by resonance. How about that? So that's what this means, induction due to length of covalent bond skeleton. Now then, orbital electronegativity. We talked about that previously, last time. You write the Lewis structure. I surely believe that you now recognize that if you're going to wrestle with questions along these lines, it's almost a given that you're going to have to do what to start the analysis? How about that? Write the Lewis structure. Structure is the most important property of any species. How many times have we said that? And it will always be true. I got a feeling that statement will always be true in chemistry. Common name for this stuff is acetylene. Anybody ever use an acetylene torch? This is ethylene, and this is ethane. All hydrocarbons. What's the difference? This, as the organic chemists refer to it, is a saturated hydrocarbon. Saturated means you cannot create any more carbon-hydrogen bonds by operating on this molecule. This is not saturated, because I can still create a carbon-hydrogen bond to this carbon atom and a carbon-hydrogen bond to this carbon atom, which would amount to turning this molecule into this molecule. Unsaturated. Now I can make 2 more carbon-hydrogen bonds on this carbon and 2 more on this carbon, which would turn this all the way into this. Have you heard anything about nutrition and food safety and stuff which relates to saturation versus unsaturation?
Saturated fat and unsaturated fat.
Which ones are considered more safe to eat? Unsaturated. Hey. Now I can't say that I'd explain that straight away, but I'm sure it's nothing too fancy. You can look it up on the web. You'll find out why unsaturated fats are more safe to consume relative to saturated fats. I'm sure it has to do with combustion of these materials inside your system as your system operates on them by reaction with oxygen to derive energy. Make you strong. Orbital electronegativity. This carbon atom is sp hybridized. This carbon sp2 hybridized. This carbon sp3 hybridized. Which of these hybrid orbital types has the greater orbital electronegativity and why? sp. Why?
Because it has 50%.
50% s character. Because we recognized, as far as atomic orbitals are concerned, in any energy level, s orbital is more stable, lower energy, than p orbital, which in turn is more stable, lower energy than d orbital. Well, that means from a hybrid orbital standpoint, the hybrid orbital type which is greatest in s character will be the hybrid orbital of greatest orbital electronegativity, which in turn stabilizes any negative charge density most effectively as a hybrid orbital. So sp is best. And if you take this all the way down to all the possible types of hybrid orbitals, considering period 3 or higher periods, sp, sp2, sp3, sp3d, sp3d2, sp3d3, d4, and d5. sp3d5 is only 1/9 s orbital in character. So that's going to have the lowest orbital electronegativity. So with that, at a glance we see this negative charge is stabilized to the greatest extent for these 3 conjugate bases of these 3 hydrocarbon molecules behaving as acids. Now these molecules are lousy, weak, feeble acids. You've got to have really strong bases react with these things to turn them into these bases. But we're making a comparison We're just trying to answer the question. How do these compare strength-wise? We're not saying they're strong or weak. We're just saying, how do they compare? This is the stronger of these three acids, or strongest of these three acids. This is the weakest. But they're really all very weak acids. Then resonance. I should think, because of your experience with resonance in 2045 and what we had you do with this stuff in 2045L, and some considerations we've already had about this stuff earlier on in our conversations, the only problem you may have is recognizing when a species exhibits resonance, when this is in fact a property of a species. And that's imperative that you be able to recognize that for any species in organic chemistry class. Because a whole lot of organic molecules have valence electron density stabilized appreciably by resonance. So you have to be able to look at the molecule, examine its structure, and answer the question, is resonance a property of these species? How do you find out? You look at the Lewis structure you've constructed, assuming that you've made one that's acceptable, and see if you can rewrite the Lewis structure. Not changing any atomic positions, not changing any bond sites, with one exception. Can I change the degree of bonding electron density at bond sites while maintaining the same overall bond structure and species structure, of course? If so, resonance. So, when we look at this, we recognize I can rewrite this Lewis structure. We talked about this, so I'll get this out of the way just for a moment. For this moment. I can rewrite this so that it looks like this. I haven't changed any atomic structure at all. The only change I made is the degree of electron density represented by my Lewis pictures at these bond sites. But then I go to the laboratory and I do studies on this thing. And what do I observe? I observe when I have the parent molecule, this thing, the acetic acid, I find a true carbon-oxygen double bond and a true carbon-oxygen single bond. No resonance here. That's true. This bond is shorter and stronger than this bond in the acetic acid molecule. That's a fact. Now I go back to the laboratory and pursue additional facts, in this case regarding the acetate ion. And what do I find out? It's almost like magic. When I take away this H+ and create the acetate ion, these bond lengths and strengths become identical. They're each shorter and stronger than a CO single bond and longer and weaker than an actual CO double bond. This bond, in fact, got weaker and longer. This bond got shorter and stronger. It's almost like magic. But the beautiful part is, it's real. How can I make a picture of this? Because from a bond order standpoint, for the acetate ion, the carbon-oxygen bond order is now 3 halves. Remember how to get bond order? I count up the number of bonding electron pairs for the bond sites under consideration, 1, 2, 3, and divide by the number of bond sites. 1, 2, 3 bonding electron pairs divided by the bond sites, 2. That's it. Then I say, how can I show this to my students? How can I draw a picture of this? And now I have to realize, from a pictorial representation standpoint, I'm stuck. How the hell can I draw 1.5 bonds? I can't do it. It's impossible. So I have to rely on these unfortunate communication devices called words. You've heard it said, I'm sure, many times, a picture's worth 1,000 words. You bet it is. But here I'm stuck. I can't draw a picture of a partial bond. How would I draw a picture of a partial electron pair? I can't do it. But I have to talk about it because the truth of the matter is neither of these pictures correctly represents the valence electron structure for the acetate ion. Because these pictures show a double bond here and a single bond here and a double bond here and a single bond here. And that's not true. There's no double bond, there's no single bond at these bond sites. Now, the remaining thing is, how would I turn this Lewis picture into this Lewis picture? You take the site of minus charge and you move electron density away from that site. The way to lower the electron density on this oxygen atom is to take any one of these non-bonding pairs, because they're all equivalent, and put them here. So let's take this one. Now, as soon as I do that, you should realize from a formal charge standpoint that the minus formal charge now converted to 0. And at this point, I've got to say to myself, this carbon I've got now 1, 2, 3, 4, 5 electron pairs. That ain't possible because carbon is from period number 2 and it can't have more than 4 valence electron pairs. So I can't stop here. I have to do this. But now I got this. Showing you that by resonance, this minus charge is really smeared over 3 atoms, which dilutes it and makes the acetic acid molecule a stronger acid than it would be if it did not possess this property called resonance. This one, for example, methane diol. You know a molecule that's analogous to methane diol? Have you ever heard of ethane diol? Ethane diol. Let me use its more common name. Ethylene glycol. Have you heard that? What's ethylene glycol? It's the active ingredient in what we call antifreeze. How about that? Okay. No resonance there. Accounts for why acetic acid, much stronger acid than this stuff. That's methane diol, not ethane diol. Now then, principle of maximum overlap. Presumably you heard about this in 2045. What you see in the notes, just one short paragraph on principle of maximum overlap, sums up, I think, all that can be said from a short to the point synopsis fashion about principle of maximum overlap. How effectively do the valence orbitals of the atoms which are bound to each other, how effectively do these orbitals overlap? Well, what does orbital overlap depend on? Depends on atomic size. Smaller atoms generally bond more strongly with each other than larger atoms. That shouldn't be too surprising to you, because for the smaller atom, the bonding electron density will be closer to the nuclei. The shorter the distance of the bonding electron density to the nuclei, the more effectively the electron density will be stabilized. The more effectively bonding electron density is stabilized, you fill in the blank. The stronger or weaker the bond? Stronger, you betcha. You stabilize bonding electron density, you're making it stronger. So we're not surprised to find out that atoms like carbon and nitrogen and oxygen and fluorine and hydrogen form particularly strong covalent bonds, even though they might even be only single bonds. Well, with respect to this, let's look at the principle of maximum overlap from a structure standpoint. Nitric acid chloric acid. Nitrate ion, conjugate base. Chlorate ion, conjugate base. And when we write the chlorate ion Lewis structure, we can see, hey, I can reduce this formal charge smear considerably by rewriting this Lewis structure like this. And I say, well, you know, this picture as it stands shows 1, 2, 3, 4, 5, 6 electron pairs in the valence environment of chlorine. Is that okay?
Yeah.
Damn right. It's chlorine from period 3. Remember the maximum number of valence electron pairs you can have in the valence environment for period 3 atom? Remember 9? There's no violation of anything. We're only limited to 4 when we have an atom from period 2. Now, nitrogen atom, nitrate ion. How's the nitrogen atom hybridized? sp2. Chlorine atom? sp3. If then this anion does in fact show a degree of resonance, which means there must be a degree of multiple bonding electron density at the bond sites, the chlorine-oxygen bond sites. There's no other kind of bond site here. Can chlorine use p orbitals for pi bonding? In this, the chlorate ion. When I write this picture, and I am curious about the orbitals which chlorine has used to be part of these double bonds. What orbitals from chlorine? P orbitals? This picture look familiar? What does it look like? 2 number 8s that ran into each other? What does this picture look like? You've seen these models? What are these models representing? P orbitals. PZ. Chemists like up and down to be the Z direction. More on that in chapter 24. We won't have much time on chapter 24, but we'll talk about it somewhat. This one? Y. And this one? X. X. These orbitals all look alike. So what do we recognize about the 3 p orbitals which are part of a p orbital sublevel if they're labeled p sub x, p sub y, and p sub z? We're looking at 3 orbitals, all of which look exactly alike. The only difference is the geometric direction of the projection of their lobes. They're all mutually perpendicular. X-axis orientation, Z-axis orientation, and Y-axis orientation. So what I've drawn here is a picture of a pi bond as a consequence of p orbital to p orbital overlap. Tell me, if this p orbital is going to make a pi bond with another p orbital, can this p orbital make a pi bond with this p orbital? Can this p orbital make a pi bond with this p orbital? Can this p orbital make a pi bond with this p orbital? Yeah, how about that? Because now they're mutually parallel. And I can get this kind of overlap. Pi bond, 2 regions of overlap. Sigma bond, 1 region of overlap. But my chlorine atom, which is sp3 hybridized, can't use p orbitals to participate in pi bond formation because they're all used up in the hybrid, sp3. But what has chlorine got, as does any other period 3 atom? D orbitals. Remember what d orbitals look like? Four to 5 d orbitals look like this. 3 Three-dimensional four-leaf clover. P orbital, B orbital. Pi bond. Just like that. So that accounts for, from an orbital overlap standpoint, the legitimacy of this picture. Now then, why is it that this acid is a good deal stronger acid than this acid? Note that for each of these species, they each have the same charge, -1. They each have 3 peripheral oxygen atoms to provide stabilization by induction. They each have a central atom which is of appreciable electronegativity, in fact almost identical. In fact, chlorine's a little bit more electronegative than nitrogen, at least as a consequence of assessment by some chemists. And this species is bigger or smaller? This one's bigger because chlorine's bigger than nitrogen. Okay? But, principle of maximum overlap. We want atoms to be kind of small and of about the same size. We have that met here, but not here, because chlorine's a good deal larger than oxygen. What else applies to this? What's the shape of this thing? Nitrate ion. Uh-oh. Nitrate ion model? Trigonal planar, nitrogen, oxygen, oxygen, oxygen. P orbitals, all with lobes mutually parallel, because this species is trigonal planar. Now let's look at the chlorate ion. What's the geometry of chlorate ion? Trigonal pyramid. So let's make another model. I don't care how you choose to orient the p orbitals on the peripheral oxygen atoms for a species like chlorate ion. There's no way that all these p orbital lobes in conjunction with d orbital lobes on the central chlorine atom, that all these lobes can be mutually parallel. Well, if the lobes can't be mutually parallel, can I get overlap that's as effective as what we have shown here? If the orbitals are parallel, and I can get as effective orbital overlap as possible. But if these orbitals are not parallel, I can't get this effective overlap. What kind of pi bond strength do I get then? Much weaker. Point? Based on PMO and resonance, resonance is now seen to be a much greater and more important property for nitrate ion than this. Planarity. Planarity and sp2 hybridization. That's what you're looking for if you want resonance to be as strong a possible property for a species as possible. Resonance here? Yes, but not nearly as strong as that. Does that support the fact that nitric acid is a much stronger acid because by resonance I'm now stabilizing this negative charge much more effectively? You betcha. Only remaining thing is, and we didn't talk about, is solvation, not salvation. I don't know how to provide that. Acetic acid. Ka value measured for acetic acid much greater in water than it is in methanol, for example. Why so? When this ionizes in water, I get this. When this ionizes in this stuff, I get this. No problem so far. But which solvent is much more electric in character? Water or methanol? Which is much more electric in character? Which has the stronger hydrogen bonding? Which has the higher boiling point? Water. And in order to stabilize the presence of ions in solution, do I want a highly polar solvent or a non-polar solvent if I'm going to stabilize electric particles, particles which have charge? What kind of solvent you want? Polar. That's it for that. We don't care much about this solvation issue now because we're only doing chemistry and water. But when you do it organic, that's important. All right. That'll do it.